All right. Well, hello and thank you for tuning in today. My name is Olivia Link and I'm a Phase 1 Aerial System or PAS Sales Manager. And today's discussion will cover the workflow and best practices of a test flight flown near the Phase 1 office in Broomfield, Colorado. The detailed results will be displayed with accuracies obtained as well as final imaging product. We will go over the ground control layout, best practices to generate photogrammetric deliverables using Phase 1 imagery, and the Ortho-mosaic and DSM images and processing times. The high-quality imagery from Phase 1 cameras has an array of applications: imagery for LiDAR, photogrammetry, ag and environmental assessment, oblique imagery, and 3D city modeling. The latest IXM RS cameras are available in 100 and 150 megapixel and contain the latest Sony CMOS chips and have a 3.76 micron pixel size, a dynamic range of 83, which yields more detail in low lit conditions, an electromagnetic high-speed leaf shutter within the RS lens. The RS lens is available from 32 millimeters to 300 and guarantees 500,000 plus actuations. USB-C and 10G data interfaces on the camera back with customizable 10G cable lengths and HDMI output with 2K video. Shown here is the Phase 1 aerial system or PAS. The components consist of a SOMAG gyro mount, camera pod, cameras, IX controller, and a Planix IMU. The IX controller acts as the central hub for the Phase 1 aerial cameras and will trigger and store data for up to 6 Phase 1 cameras. The controller manages the gyro-stabilized mount, GNSS IMU, flight management system, and runs the IX capture application. The IX controller has a 28-volt DC single power input connected to the power source with a locking power connector and a max consumption of 220 watts. The data storage consists of an SSD with ultra-fast writing capability up to 500 megabits per second. As seen in the image above, the IX controller sits in a Planix IMU. The installation time from the system in the shipping containers to installation and testing a flight plan in simulation mode can be completed by one person in under 25 minutes and has a total weight of 42 pounds. The complete PAS with 2 cameras for 4-band imaging, SOMAG gyro stabilized mount, a Planix PAWS AV210 with POSPAC license, Phase 1 flight management licenses, and IX controller runs around $335,000 US. Shown to the right is the SOMAG CSM40 with the RGB 150 megapixel camera. With IX controller and flight management software, this system runs about $215,000 US. The IX controller in this configuration will be mounted off to the side and has a built-in mounting plate which can be secured elsewhere in helicopter or fixed-wing aircraft with customizable cable lengths. Here we have the PAS workflow diagram used for acquiring the local mission: flight planning, image acquisition, and post-flight data processing. The flight plan is generated through IXPlan, which is TopoFlight based. For more information, please visit the webinar section on the Phase 1 Industrial website with the latest FMS updates and complete overview of IXPlan and IXFlight. The flight plan folder is then installed on the IX controller and open in IXFlight. This displays the flight plan mission to the pilot and operator displays. IX capture application is ran during acquisition to control camera settings and display the per image histogram. Collection can run in an auto exposure mode, which is convenient for a single operator pilot mission, or manual mode, which an operator can adjust camera settings as needed. After the mission is complete, the images and PAWS data are ready for processing in IX capture and a Planix POSPAC. TIFFs, EO, ground control, and camera calibration can then be imported into various photogrammetry software packages to generate DSMs, DTMs, and orthomosaics. And here we have IX capture, which the camera connection and SSD storage capacity can be checked within the IX capture application during flight. IX Capture application displays the photohistogram as images are taken and allows for camera settings to be adjusted for and during acquisition. Here displayed on the left is the RGB image in histogram, as well as the near infrared with the histogram. In IX Capture, you'll also process your images from the raw IIQ format to TIFF. There are two types of products for photogrammetry workflows, corrected and uncorrected images. IX Capture 4-band product generates corrected images in 3 or 4-band stacks. RGB-only images can be exported as uncorrected or corrected images. For the use of uncorrected images, all the parameters provided with the calibration certificate should be used. For the corrected images, only focal length value from the certificate is needed and all parameters are suggested to be zeroed. A digital version in text file is delivered with the cameras. If you find yourself without the digital calibration file, please contact Phase 1 with the camera serial number and we will provide you the text file right away. Here is displayed the principles of orientation, 3 body frames involved. X is always direction of flight unless the IMU is rotated and then should be noted in the processing. Suggested processing of RGB images is from the uncorrected format and allow preferred photogrammetry software to calculate the GNSS antenna offset or set to 000 for your XYZ. If camera is installed such that camera y-axis is the flight direction, then put degrees in this field. Also recommended to enter the camera calibration values, not to enter the camera calibration values manually. Use the digital text file and the photogrammetry software packages. Should you not have the digital version, again, please let us know and we can provide that for you. For the local flight, we were based out of the Broomfield office here in Colorado at Phase 1 office. The flight speed average was 120 knots, 52 degrees out, solid ceiling at 17,000 or solid overcast. The system installation took about 15 minutes and the total flight time with turns was 35. The area collected consisted of 4 flight lines flown at 9.2 centimeter GSD or 4,000 feet AGL or 9,443 feet MSL, and was flown again at 120 knots with the PAS 150, which consists of the RGB and NIR camera with 50 millimeter lens, the SOMAG DSM 400, a Planix Pause V210, and the Phase 1 flight management system. There was a total of 60 images, which totaled in 20 gigabytes after processing to TIFF from the raw IIQ file, and took about 1 hour and 15 minutes to process all 60 images. The lens distortion was not removed from the images, and third-party photogrammetry software derived distortion values. There was a total of 16 surveyed ground control points that were set and measured and laid out in the CalQC suggested method, as that's a module in PausePack. After running the ground control through AT, the ortho and DSM accuracies were about 9 centimeters and the XY combined circular error of 8 centimeters on average. Shown here is the ground control point layout for a bore site calibration according to the Planix methodology. 3 ground control points per corner plus 4 ground control points at center of the block. Again, here we have the layout displayed within Trimble info, and here's our photo identifiers, and the ground control points were collected post-flight to ensure no obstructions were over the points. The first software program that we used to run the data was Pix4D, and we'd just like to say thank you for them in supporting our efforts. Here we have the Pix4D Ortho, which took about 2 hours to run. The DSM extract took about 1 hour to run, and these are just screen grabs from viewing the data in Global Mapper. The DSM to DTM ran about 30 minutes, and the final mosaic took about 2 hours with total processing time of 6 hours. The RMS error was 8 centimeters, and the accuracy in the X and Y was 6 and 8.5. The next software that was used was PCI Geomatics. And here is the ortho that was generated. And ingesting imagery to Ortho Engine project took 2 to improve AT at the tie points and ground control points, took about 33 minutes. And here we have the DSM, the extract to DSM took about 60. And the DSM to DTM processing took about 38 minutes. In total, the ortho and mosaic generation was about 2 hours. And here we have the DSM ortho comparison. Next was the Trimble Info software. And, oops, sorry, here, I'm losing my spot. Sorry about that. Again, in the PCI software package, we had about a 9 centimeter mosaic and a 9 centimeter DSM with a combined XY of 8 centimeters. Here we have info ortho generation with ground control laid out. To ingest the imagery in Applications Master was less than 5 minutes. The improvement of AT with tie points and 16 ground control points was about 45 minutes. The ortho production or ortho master ran for 10 minutes, and the Ortho-mosaic or Ortho-vista ran for 20. Here's the info DTM, and finally the info Ortho-mosaic, which the extract DSM using Match AT took about 1.5 hours. The extract DTM, 15 minutes, with a total processing time of 3 hours. And again, about a 9 centimeter mosaic and a 9 centimeter DSM. And finally, the last software used was Agisoft. And here we have the true orthophoto, the match photos with highest 7,900 tie points ran for 3 minutes and 30 seconds. Aligned cameras was about 5 seconds. And here we have the DSM, which providing the ultra high quality map or was about 7 hours. And here we have the digital surface model detail. And finally the DEM or DTM, which was 32 minutes. And in total, again, 9 centimeter ultra high DSM and a total of 9 hours and 45 minutes for processing. And that concludes the presentation. A big thank you for the companies that process the data for our test site. And please submit your questions on the GoToMeeting message box.
Hey, Olivia, this is Paula.
Hi, Paula.
Thanks for the webinar today. It was absolutely fantastic. One question I've just got is, are the bore sites done at your local office?
You know, actually, Lewis kind of is ahead of that. So let me hand the mic over to Lewis.
Hello, everyone. Please submit your questions.
Yeah, there was just one asking if the bore sites were done at the local office.
Excuse me, repeat again.
The bore site collections were done at the local office?
Oh, yes. Well, the ground control points for bore site calibration were acquired using base station, an SPS 985 Trimble, and was corrected using VRS now, which we have coverage, luckily, in Colorado. The methodology can be explained later if you submit your direct emails, which was a quite sophisticated way to guarantee the accuracy of the ground control points and later on the quality control for bore site calibration.
Okay, thanks, Lewis.
Thank you.
That's all. I think you've answered all the questions, Olivia. Obviously, if anyone wants to get in touch with you, they can email you directly. So thank you very much.
Thank you, Paula.
Thanks, guys. Bye.